Hello everyone. So I can see here four people are waiting here actually. Okay. Um, you can ask your question. This is all of you know that risk-based engineering course, and this is a question answer session, and I'll be happy to answer your question. Okay. So I should get your question either in text form. Um, so in chat box, you can put your question and I'll be able to see your question and then I'll answer it. Actually. Okay. So please go ahead and ask question. In the meantime, if I'm not able to see any question, then I'll continue my general talk on this course that is risk-based engineering. Uh, this course has been designed for professionals, scholars, student, and practitioner. I would say industrial practitioner. Good evening, Vidya Sagarji. How are you? So you can ask your question and please name the week and topic that you are asking, so that I look forward to a question from you or your feedback, whatever you want. It is a session which is free. You can ask anything or suggest anything. So one I saw Mr. Vidyasagar TEC. I don't know what TEC means. Okay. Okay. So in the meantime, I'll go ahead and I'll just give an overview of the subject and why you should be. Probably you have taken a very good decision, because any job, engineering job you do, or even finance also, or any other things, social things, there is an inherent component of risk. Why inherent component? Because randomness is there in all the walks of life, our life, and as long as randomness is there, there is uncertainty, and uncertainty associated with the risk, and that probably requires, because even if I do some calculation, and if I give a point, like we are in our academics, we are used to giving a point estimate for an answer. But then there we the forget, or we don't consider the uncertainty associated with a parameter, whether it is a load, whether it is a stress, or whether it is a dimension. Even though we write a dimension, something like this, material property also, when we take into account. So what happens is, when the product is designed, you'll see that it's a failure. There is an uncertainty about when it will fail or how long it will operate. Let's say in positive, what is the reliability? Now, reliability also, again, we give a point estimate. So, a point estimate is okay if the answer we can absorb that uncertainty or risk. But there are certain situations we are not able to capture that uncertainty. Okay, so that's how it is. Okay, so here there is some suggestion that I should introduce myself. Okay, I assume that all of you who are attending the risk-based engineering course, they know me. Nevertheless, I am Professor Prabhakar V. Varde, and I am the instructor for this course on risk-based engineering. And there we started with the first module, like it was general, that introduction sort of thing to the subject. And then finally, we went into various reliability configuration, system analysis, and then finally, human factor analysis. Some time we focused on electronics and structural component of the, because this is an interdisciplinary subject. So it touches all the branches of engineering, whether it is electrical, electronics, mechanical, any subject, thermal hydraulics. And that's how it is very important that we understand the subject. And at the end of the day, whenever you design a subject, they design a component, or you operate certain situation or plant, then uncertainty and risk component is inherent to the system. Particularly if the system becomes complex. Complex means what do we? A lot of components they are interacting with each other, and every interaction gives new results. And then human factor is involved. Then uncertainties are there. So the predictability in the results has to be addressed, and that's why this course on risk-based engineering it is there. Only one component, as far as the reliability is concerned, the state of art is not, so especially for critical system, though a lot of softwares are being developed all across. But when we talk about the critical safety critical system, the software components they sort of the uncertainty of their performance is little higher. So maybe in many systems we can absorb because it is an issue of reliability. But wherever it is a issue of safety, then at least safety critical industry is little careful on having a component where software is one of the thing. And there we do not like digital systems. So we do not accept those systems unless until we have some deterministic provision wherein redundancy is there in actuating a safety function. So depending on software or digital alone is sort of even now with a lot of cares they are being adopted into the safety critical system. They have become sort of part of the mainstream, but with a lot of redundancy, diversity, and things like that. We so that is the case. So software, and then since you are studying this subject, there are certain areas like common cause failure. Common cause failure is a very important thing because the kind of redundancy you have, it gets knocked off if one component failure or one situation like flooding, fire, or even smoke, humidity. So one these are all environmental conditions, and other conditions are you have three component redundant component, and they are having same material, same design. So if one component fails, there is a possibility other two will also fail. So it is a common cause. And worst common cause is human action inducing a common cause. So human factor, common cause, and software. These are the three areas. Whenever we do any project, we have to focus on it actually. So we have to be very careful that we are accounting, and whichever say when we do a risk analysis, one of the important point is your data. And there is a simple observation about data. If the data is not good, the results will be fuzzy, not clear. So you have to, if my experience is right, you have to work on your data also. Okay. If any questions are there, let me say, please ask your queries to sir. Okay. So now my manager is asking you that if you have any question, you can ask. I'm giving the background just because I have time here. So in between, if you have a question, please ask the question. Okay. Okay. So Mr. Vidyasagar, since you are the one who came first, you have any specific question? So please ask. I'll be in the meantime, I'll go on giving you or reinforcing my thought, or rather, background, so that you carry, at least people who are there, they can carry this thought with you. And these are small things. When you do the modeling, you have to bear these things in mind, actually. So these are something like, higher level points. As I said, common cause failure and the human factor, digital system, software component, and digital system also. They are very complicated now. Earlier, we used to have solid state logic, in which there used to be almost like right from 10, 20 to maximum 1,000 transistors. Okay. But now millions and billions of gates are there. Chips have become very complicated. The kind of computer chip or any system chip, FPGA, field programmable gate arrays, if you see, now there are millions of transistors there. So why there are reliability issue? Because the distance between two connectors or two path is current carrying path is small, and it has reached the design limit actually, that is one thing. And then heat dissipation, okay, and then so let's say dielectric breakdown, hot carrier effect, since they are condensed into a small space, these kind of things. So you know that electronics, dielectric breakdown, hot carrier, and these 3 4 mechanisms, they are there, they become prominent actually, leakage current. Okay, and when you want to start the electronics reliability, you should be very careful with the capacitor. Capacitors are the component which are important from safety. That means fire, especially for power electronics. Okay, 500 microfarad this capacitor, and then IGBT are the component. Third one is solder joint per se, because solder delamination and all these are the so and the issue there is thermal cycling. Thermal cycling is the cause for failure actually. So this is about electronics, and as far as the mechanical the components are concerned, so far the things were being managed with the safety, safety ratio or factor of safety and all that. Why? Because in those days the mathematics was not all that strong to characterize the uncertainties associated with the parameters. But now the science has advanced like anything. So now we can draw a distribution of stress, distribution of strength, and we can understand. And the net result is system become less bulky, well understood. And then since we know that there is very little overlapping, that is failure probability reason, or there is no overlapping, so chances are less. Here we should see this overlapping of this thing, stress strength. They are depending on our strength. If suppose there is a third component or a third stress level, so then also they overlap more actually. So the analyst has to remember these uncertainties. So this is what I would say, and then I would say that if I don't talk about this, my lecture will not be complete, or our interaction will not be complete. This area is called probabilistic risk assessment. If you take the other side, it is a deterministic safety assessment. Okay, so the probabilistic safety assessment has come or is relatively new, but deterministic safety assessment is a traditional approach to safety or risk, where conservative design and safety margin, okay, factor of safety, and then having redundancy, diversity, they form the core of design or operation or even maintenance actually. But probabilistic risk assessment has come. Why it has come? Because now data is available. Okay, so if data is available, then we can have a probabilistic component to our analysis. Okay, so what you do is you see what are the events that can happen into your system, which will destabilize your system in terms of reliability or safety. And then finally, especially we model for safety, risk and all. So, and then second thing is, what are the defense provisions that they are there? So as long as defense provisions, they come and actuate, there is no problem. But the moment the defense, because, as I said, there is a variability. Whatever, even if you have the best of the understanding, but there is always a new component. And that's how the accident happen, because systems are designed with all due consideration, taking into account what are the almost postulation, but always a new element comes in, and then and accident don't happen just like that by one component failure. It happens because of multiple events, unsafe events, and then only you lead to why multiple events, because you have a lot of redundancy, diversity, and things like that into the system. And that's why we see a robust system nowadays. whether you see your computer, or maybe some failures are there, but okay, you yourself surprised, whether you shut down or don't shut down, it keeps, the moment you open it, it start giving you service. So it is a result of the best practices into the design and anticipation of events, whether it is a safety or reliability related events, and that's how we have more reliable system. Thousand or more than thousands of components are sitting on one system, and still the things work very well. So that means the failure rates of individual component is going to vary, especially if they are all connected, assumed to be connected in series. Then it is a something that you are operating a very credible system, which is giving you a service. So, as far as the our course is concerned, uh, focus focus on human factor also. Maybe the human factor is a subject which is evolving, I would say. Okay, but compared to some 10-15 years ago, now there are standard methods are available, wherein you can plug in your requirement, um, have some factors like mil standard 217 F or even plus. These are very streamlined method. They're so if you can use it, you'll find yourself. They are ready Rockner type you have to use, and you have to analyze your system. Yeah, we have a good framework, but still, as far as reliability is concerned, the science has to go to the physics of failure. So the notion of one of the module is prognostics and health management. You all know that. That will come little later, maybe 1 or 2 weeks. So there the objective is okay. Failure probability is good. It is good for identification, prioritization. You can line up systems, but then the industries, they are interested in, if a component is failing, or then you should get a symptom. You should get a indication that it is degrading, and then you should get an indication how long it will operate. So for that, there is a concept, and this is picking up greatly. It's called remaining useful life. So if it is a critical component or system, then if you have estimate about its remaining useful life or trend, how it is degrading. So always, most of the component, the moment they go to their threshold of failure or critical parameter in mechanical engineering is called critical crack length. If it is a fracture, so how much life is available? So these are very useful thing, because whether this component will work, the industries they operate, day and night. So your next shutdown is, let us say, 1 month away, and you are interested, I don't want to shut down now. So will it cross my next shutdown, or I'll take up this into the next shutdown, or I have to take it today or tomorrow or whatever. So you can do a PHM, prognostics and health management, so that you once prognostics are there, you can activate your management plan, and you can take the right action. Actually, that also means spare part, manpower, resources, gadgets, fixtures. But suppose if the component suddenly fails, and you knew there was degradation, but we didn't know, then you are at loss. You lose on reliability, that is deliverable of the system. At the same time, it might have a penalty in terms of more risk. So by PHM, you save on this actually. Okay. Okay. So, okay. So I'm waiting for you to ask question, because this is the right opportunity for you to ask question. You will be approaching your exam. Okay. So better we utilize this time for questions. You can ask question. I mean, it need not be a very. I mean, even if you have a small doubt, you can ask the question. No problem. we are here to interact. We are here to interact. You can even express your opinion about certain aspects of lecture or question. I think my students, they have understood everything, and are probably, uh, they have not understood, or they have to yet start their preparation. This is what I am getting. I would like to believe that you understood everything and you are busy preparing for your. I have one of the recent weekly assignment. There was one question in which there was a and get there was a query also on that, and diesel 1, diesel 2 failure probability something, and the answer was 10 to the power minus 6. If I'm not wrong, some 5.23 or 10 to the power minus 6. The range was given. There was a confusion because the exponential term was negative minus 6, and it was a editorial thing. So I'll ask my NPTEL staff how to address this type of things. But this is one message that you can carry forward yourself. So we our objective is to see that you get the good lessons on risk and reliability. That is what, and that is what our aim is actually. So we'll see to it that justice is done to your hard work. Uh, you know. So this is a question by Mr. Sano. Respected sir, black box technology is not understood. Okay, this is one question. Wait, sir is coming back. Okay, of course, many things go beyond because of our low mathematical background. Okay, very good. Okay, so Vidyasagar ji, the black box technology, this word probably we have used for artificial neural network. Why? Because the uh, the inputs are fed to the ANN, okay, and the output comes out. So and there is a in between activation function. So earlier, what is happening inside? I'm talking about 90s and all. What is happening inside? That was not clearly understood. So we used to call it a black box, ANN. What is happening inside? Input, output, and the result used to come. But now, with the knowledge that is growing around, what is happening at the uh, uh, input level, we know because we fed the input. Activation function. So what is happening is, I think I taught you that concept of pre-processing, filtering, okay, those things. So there first is we understand the data itself. Otherwise first you don't understand the data and then you feed it, and then finally then what the activation function is doing. So what we do is, in the first layer itself, we tape the output, then we tape the output at hidden layer the thing also. So then we have an idea of what is going on. But the question of how, when, and how much, those sciences are really evolving. So the simple in simple term, if I do a mathematics, linear mathematics, okay, then I'll know y is equal to mx plus c. So what I know the output, y, what is the value of y if I know mxc. But here, if I give value of this thing in various vectors and all that, and how they interact among themselves, this was something a gray area. So one is that black box approach, and second thing, you are saying कि mathematics is. Let me tell you, at every stage of my lecture, I was ensuring you, because I knew that engineers they do not like too much of mathematics. So in my first lecture itself, I have promised you that I am keeping mathematics to the minimum. But okay, that I tried. That was at my level. But one of my teaching assistant, she told, "Ki, even this mathematics is," but then, my objective was that when I'm teaching you, you should get all like a toolbox. You don't have to go around. So even if some mathematics is crept in, probably with little effort, because at some point of time, even we were sitting in your position, okay, and we had to learn. We have to come out of our comfort zone and understand different tools and methods. And I have seen in, like, in our young age also, there are some student, they will pick up a subject, new mathematics or a subject within 10-15 days, and then they will start using it in our. So what we, in short, we mean is little efforts are required. You are all very lucky because you open your internet, you put the keyword, and a lot of information flows. Earlier there are books. Now which book will give me answer unless until buy the book, and you may not have you zero down a correct book actually. So you are very lucky. Let me tell you one thing. All of you have a reasonable amount of intelligence. That mathematics will not be a stopping factor or obstruction for you if you make more efforts, because everybody in this field, they learn. And now the bigger part of the risk analysis of fault tree, event tree, there, if I have to be very frank with you, it requires a multiplication, it requires a logic, it requires, suppose if I don't have data, Bayesian updating, which is not a rocket science, okay. If it is a Markov model, again you can do it. Multi-state systems, if you utilize, you can do it. Only thing is you have to invest little resources. So please overcome this difficulty of mathematics. What I gave you was, I was conscious, because in my first lecture I had promised you I will not teach, I will not introduce a lot of mathematics here. You try to understand the distribution. I'll give you the easiest way. You understand the distribution. You learn to draw the fault tree of your system, whatever you have. You draw event tree. You generate the accident sequences. You estimate their probability, and that will be your toolkit's central module. That itself will answer many things. Then you get on to the, again, distribution. Try to understand the uncertainties, log normal distribution, normal distribution, okay, F distribution. If you have data, discrete data with you, okay, understand what is discrete, what is continuous data. Understand common cause failure. It doesn't require a rocket science. One component failing, many redundant components. So where is the mathematics? And there, those formulas are all empirical. Beta factor model, MGL model. They are all very simple model, but they have very high impact. So you have to be very. Then you require a domain knowledge. So how your domain is sensitive to this kind of factors. So good that you asked that question. I can assure you that you will pick up if you devote reasonable time, understand the distribution, and see, there are software which enable you to draw the fault tree, event tree, and you can take student version of these softwares, like commercial software. You will not be able to take a printout, but you will certainly know what is AND gate, what is OR gate, how to draw that, and how to simulate, and how to generate the result. They don't allow you to take a printout. I'll not name any particular software, but you can see for PRA software, and you will get those things. They are available freely, and you can use them actually. So like that. Okay, so Vidyasagarji, what you are telling next is, fully agree what you said about my status. You try your best. That is the best bet you can have. Since you are asking this question, I know you are very serious about the subject. And if you are serious, nobody can stop you. And once I was operating a mega system, but this subject, I found it so interesting, and I built my academic empire on this. If I have to call my so many publication and all that. So yeah, so I think you got this thing. There is nothing. You can ask question also in between. These sessions are not required. You can ask question, because the next session will happen somewhere on 14th or 15th. So till that time, you'll be very close to the exam, and we'll be happy to answer your question. So I think I'll close this session. If no other person is there to ask question. Bharti madam is there. Yeah. So let us close this session. Though we thought up to we'll have to go up to 7 o'clock, but I think since no new student is joining or candidate is joining, we'll close the session. Thank you very much. And Vidya Sagarji, thank you. You are the lone person the session this session was dedicated to. And please show a good progress. You will feel my promise that in future how useful it will be for you. Thank you very much.